So once we have fitted our linear model to the data, or in general our regression model to the data, it is important to perform a residual analysis. This residual analysis will verify that the residuals actually meet the assumptions that regression is doing. In particular, there are two very important assumptions that are the normality of the residuals and the independence of the residuals. And independence is twofold. So first, independence between residuals, and also independence with respect to the predictor variable. Okay, so we will do this presentation by showing simulated cases in which we know the underneath ground truth, and then we will check whether the regression actually reflects what we know. So here, normally in this blue box, we will have how we generate the data. So we have here 1,000 samples of a variable that has x, has mean 10, standard deviation 1, and then we are collecting 1,000 samples, and so this is the size of a vector of a matrix, so it is n times 1. And then once we have the x that we have randomly chosen, then we will construct a y, and y is a function of x. It is a linear function of x where we have fixed the values b0 and b1 plus some noise, and the noise has a given standard deviation that in this case is 0.1 and the same size as the matrix X. So this piece of code gives us the X, Y observations. Then we fit the model, and what we observe from the model are the coefficients are 1.01. The true B0 was 1, so this is very close. Then for B1 we have 3.999. The true value was 4. So these two estimates are very good. They have very good p-value, meaning that the model is pretty sure that these coefficients are not 0. The R squared is also very high, very close to 1. The p-value of the model is very good. And also very importantly, the root mean square error, that it is a biased estimate of what is the standard deviation of the data, but if you have enough data, the bias you don't notice. So the root mean square error is very, very close to the true standard deviation. So the true standard deviation was 0.1, here it is 0.0999. Okay, so this would be the ideal case for performing a regression where you have very small noise and quite a lot of data. Okay, so now the residual analysis takes the residuals. A reminder, those are the differences between the observed y values and the predicted y values, and we make a histogram of it. So they should look like a Gaussian. Also, we are making a QQ plot. A QQ plot is another way of representing this data, this histogram, and in the QQ plot, the residuals should fall within this line, that is the identity line. Okay, identity in some space, not here in this plot. Okay, so now we can also plot the residuals versus the fitted values. So this is residuals versus y. It is also interesting to perform residuals versus x, and also residuals versus the row number, so that we analyze as a function of the order so whether we see some pattern, and we shouldn't see any particular pattern in any one of these plots. So this is good. This is an ideal case. Okay, so now let's move on to a less ideal case. So less ideal case, we have a small noise, but we have fewer data, much less data. So here we only have 10 samples. So in these 10 samples, the model is still the same, the standard deviation is still the same. Now, when we do the regression, the estimates of the B0, B1 are much worse. So you see B0 is 1 in reality, but we have estimated 0.74. It is not far, but still it is not. It is much worse than before. And for B1, the estimate is relatively good, and the p-values, the p-value for B1, beta 1 is very good, but the one for beta 0, although significant, but it has deteriorated a lot if we compare to the one where you have a lot of data. So with less data, what comes out is that it is more difficult to show that your parameters are significant. Still, the root mean square is relatively close to the true standard deviation value. Now we observe better the bias, so this root mean square error is much further than it was before from the true standard deviation, and the fact that we have less data makes this bias more apparent. Then the R squared in this case, and this is just a particular example, it doesn't need to be always like this one, but in this case it's very good. The p-value of the model is very good. Okay, so now we do the residual analysis. Now the histogram doesn't look anymore like a Gaussian, and the reason is that we have very few data to realize that the residuals are really Gaussian, but still when we look at the QQ plot and the other two plots, the residuals versus y and the residuals versus the raw number, and we are missing here the residuals versus the predictor, but we don't see any particular pattern. Okay, good. So now we have much more noise, and we are back to the case with many data. So with many data, so the B0, B1 parameters are still the same, but now the standard deviation is 100 times larger than it was before. So now the estimates, the one for B1 is relatively good, that p-value is very good, but then the one for B0, the p-value is very high, meaning that the model is not sure whether this B0 is actually 0 or not. So in principle, following our rules, we should remove B0 from the analysis, because we are not sure that it is really there. And we can also see that B0, despite the fact that we have a lot of data, B0 is very bad. So the estimate is very bad. The true B0 is 1. Here we have 2.29. So now the R squared is very bad, and the meaning is that the variability explained by the model is just a small fraction of the overall variability that we have. So the variability caused by the line is much less than the variability caused by the noise. But it doesn't mean that the model, that there is no relationship between y and x. There is a relationship. This is captured here by the F statistic. So the F statistic tells you whether the model is really explaining something, so it does. And then the root mean square error, that is an estimate of the standard deviation, in this case is pretty good. Okay, so now let's do the residual analysis. So the residual analysis, the residues seems to follow a Gaussian distribution. The QQ plot, we don't see any specific pattern, and the same in any of these two plots. Okay, another case, large noise, few data. This is really a very bad situation. So the standard deviation is 10, the model is still the same. Now our estimates are really bad. Maybe the one of B1 is not so bad, but still the model is not sure that the B1, that there is a relationship between Y and X, a linear relationship. So the two p-values are pretty high. We should reject we cannot reject the hypothesis that B0 and B1 are really zero. The root mean square error is really biased because of this lack of data. The R squared very bad. The F statistic tells us that it is not sure that the model is really explaining anything. So if you have a lot of noise and very few data, you are in a really bad situation. Then, for instance, here we can note that there is a point that really deviates a lot from the regression line, and this point is actually shown in the QQ plot. So now we see that the data really deviates from the identity line. That wasn't the case in the previous examples. So they were pretty close to the identity line. They're not exactly at the identity line, but they were pretty close. Small deviations at the extremes are relatively normal, and what you don't want to see are extremely large deviations as the one you have seen here. So here in the other two plots we don't see any specific pattern, so in that regard the data is not that bad, and that is a good reason for that, because actually the residuals were Gaussian. So these large deviations is something you should expect if you have very few data. So if you have very few data, then the mean and variance that you estimate from these very few data is probably very far from the mean and variance of the true distribution, and that is why you observe these large deviations here. Okay, so now we have another case that is similar to the one of C3. So C3 we had a lot of data but also a lot of noise. So now we will have the same amount of noise, but now the standard deviation of X, instead of being 1 as in the case C3, in this C3 B's, what we will have is X extending much farther. So now in the previous case X was going from 7 to 13, now it goes from -20 to 40. But we have the same amount of noise, but now B0, B1 become much closer to the true values, and we can see that, for instance, here we had B0 that we could not reject the hypothesis that B0 was 0, but now we can clearly reject it. The estimate is not still too good, but we can reject the hypothesis that it is 0. And now the R squared has dramatically improved. So that gives us another clue about how regression works. So when you have large extents for the range of the predictor variable, it is easier to show that a line is or a regression is significant. Actually, this has to do with something that is called the signal to noise ratio. So the signal to noise ratio is what is the variation in Y. What is the variation of the residuals compared to what is the variation of the predictor variable. So here the predictor variable has very low variability, and the noise is some particular value, but now the noise keeps the same value, but now the predictor has a much wider range. So it is easier to show that a regression is significant when this variation of the residuals is relatively small compared to the variation of the predictor. Okay, so now let's put another example where we have a small slope, and we will compare them or analyze it in the presence of large and small noise. So here we have the small slope, and here we have large noise, here we have a small noise. You may look at the y-axis, so here it goes from 20 to 90, here it goes from 49 to 57, so there is much less variation in this example than in this one. So now the intercept here is clearly different from 0, but because it is 50, it is much larger than 0. But the small slope cannot be detected in this case, while in this other case it is clearly detected and with a reasonable accuracy. And here again the root mean square errors are good estimates of the true standard deviations because we have a lot of data. And here is the R squared. So the R squared means how much, what is the fraction of the y variability that we can explain with our model. It is very small, even that adjusted R squared can become negative because of the penalization. The F statistic tells us that it is not sure that the model is really explaining something, but here in this other example where we have much less noise in y, now it is sure that the model is really explaining anything. Okay, so this points out again the idea of signal to noise ratio. So here the variability of the residuals compared to the variability of x is much smaller than in this other case. So normally it is defined as the variance of x divided the variance of noise. So now we have even smaller noise, so now it is very easy to realize that b0, b1, that they are significantly different from 0. We have good estimates of those two values, and the R squared is really good, and the p-value of the whole model is good too. Okay, so now here we have another model, but now we are breaking another assumption of the regression. That is that the only relationship between y and x is the one we are analyzing. So we are analyzing linear relationships, so beta 0 plus beta 1 x, but actually the true relationship takes this beta 1 and multiplies by x squared. So our model does not really feed the true generation model. And now what we observe is that the b0, b1 estimates are completely wrong, completely wrong, but the R squared is relatively good. The F statistic is also tells us that we are explaining the data very well, but the mismatch between our true model and the model we are analyzing makes that this regression doesn't really identify what is the generation mechanism of the data. So if you completely misfit your model, misfit in the sense that the family of functions that you are analyzing does not include the true generation model, then your estimates can be good. So can be good in the sense that they can predict the data in the range you have analyzed, but it doesn't extrapolate at all. So if you try to analyze the data outside this region, you would make completely wrong predictions. Then we can detect that a bit with the residual analysis. So in the residual analysis, we see that there is a long tail that is not well explained by the data, by the model. So the right tail that corresponds to this part of the data, that there is a systematic error that makes the residuals to be positive. And this is shown in the histogram, this is shown in the QQ plot. Now we have kind of V pattern in the plot of residuals versus Y. With respect to the row number, we don't observe anything special, but we would observe also the same kind of V pattern in the residuals versus X. So this is all for the residual analysis and today, and see you next time.